Okay, today we're going to be talking about the about simplifying, adding, and subtracting radicals. And the first thing we want to talk about is the product rule for radicals, and that is this right here. It's pretty similar to the product rule for exponents, but we're dealing with radicals instead. So this the nth root of a times the nth root of b is equal to the nth root of a times b. Or we can get rid of that dot in between. Means the same thing. So the nth root of a times the nth root of b is equal to the nth root of a times b. This is, I said it's similar to the product rule. What I mean is that it's very similar to the distribution rule for exponents. So to give you an example of this, just to show you this in action, let's say we have square root of 32. Okay, so the square root of 32. So square root of 32 is not a rational number. You can't. There's nothing that, like 4 times 4 is not 32. I mean, that's 16. So there's no number that, like, whole number that when you multiply together you're going to get 32. So 32 is going to be an irrational. Sorry, the square root of 32 is going to be an irrational number. But let's write it this way. Let's write it as the square root of 16 times 2. Okay, so square root of 16 times 2, well, now we can apply the product rule for radicals and rewrite this as the square root of 16 times the square root of 2. See, just like we separate, these can be separated, so you have square root of 16 times 2 is equal to the square root of 16 times the square root of 2. Okay, so now we have something that we can actually work with. So square root of 2, that's an irrational number. We can't simplify that any further. But the square root of 16 is equal to 4. So we can say that this entire expression is equal to 4 times the square root of 2. And in fact, this is the simplified version of the square root of 32. It's 4 times the square root of 32. So let's go on to another example just to show you something a little more, just a little bit more complicated. So say we have the square root of 98. Okay, so we do a prime factorization of this, of 98, and we'll see that it's equal to 2 times 7 times 7. Okay, so 98 is equal to 2 times 7 times 7. And so that means that the square root of 98 is equal to the square root of 2 times 7 times 7. So I can rewrite this as the square root of 2 times 7 squared. And now this 2 times 7 squared can be separated into two radicals. So square root of 2 times the square root of 7 squared. And now, what's the square root of 7 squared? Well, we don't even have to know what 7 squared is. I mean, it's 49, but we don't even have to know that much to figure out what the square root of 7 squared is. It's just 7. So this is going to equal the square root of 2 times 7. Although, for convention's sake, we usually write this as 7 times square root of 2, we usually put the whole number in front of the radical. So here, let me scroll over to the right a little bit so I can take up a little bit more room. So this is equal to 7 times square root of 2. Okay, so that way I have a little bit more room to work with down here. So now I want to do this one more time, this same problem, but I want to do it in a slightly different way. I want to visualize it differently. So instead of, well, I'll just show you. So take the square root of 98. Okay, so the square root of 98, you can again, just like up here, you can rewrite as square root of 2 times 7 times 7. 2 times 7 times 7. But instead of going through this hassle right here, what I'm going to do is I'm going to notice something. Okay, so I have a pair of 7s here. So what I'm going to do is cross out the pair and move the what's being paired to the front. So let me show you better the way I'm doing it. So let's say I have, okay, okay, so I'm crossing out these two 7s, but I can't do that without first putting a 7 out front. So for every pair that I have underneath the radical, I could cross out that pair and then take whatever's being paired and put it out front. But then I want to write it more cleanly so that it can be read more easily. So it's 7 times square root of 2. And see, of course, that we have the same thing over here. Now I want to try to explain this. All I'm doing is I'm doing the same thing over here. So you notice I have a pair of 7s that that turns into, instead of square root of a pair of 7s, it becomes just 7. So I'm crossing out a pair of 7s and bringing it out to the front. And then, of course, I want to write it more cleanly, because otherwise it can be a little bit hard to see exactly what's going on. So that leads me to this algorithm, this not necessarily an algorithm per se, but for a square root. Let's scroll back to the left. For a square root, you want to write all numbers as their prime factors. Oh, line break. Write all numbers as their prime factors. You want to, and then for every pair, write one of the thing that's paired outside of the root and cross out the pair. I'm going to have to, okay. So write all numbers as their prime factors, period. And then for every pair, write one of the thing that's being paired, and then outside of the root. Cross has 2 S's. Okay, so for every pair, write one of the thing that's being paired outside of the root and cross out the pair. And then, of course, as the final point, you want to rewrite it cleanly. Because if you rewrite it cleanly, there's less of a chance that, well, there's a better chance that the person who's grading it will understand it. And so this is just for square roots, but what if it's nth roots? So for nth roots, it's the same, but instead of pairs, you look for groups of n factors. I'm going to have to put a line break in there somewhere. instead of not pi, pairs, you look for groups of n factors. So, okay, so let's go over this just briefly one more time. So, for square root, you want to write out all the numbers as their prime factors, and for every pair, write one of that things that's being paired outside of the root, then cross out the pair. Then rewrite it cleanly. And by cleanly, I mean you get rid of the things that you crossed out. Rewrite it without those things. But if you don't have a square root, if you have an nth root, you do the same thing, but instead of looking for pairs, you look for groups of n factors, n amount. So, let's say, for example, you have the third root of 54. So, 54, if you factor it out, is going to be equal to, so the square root of 54 is going to be equal to the square root of 2 times 3 times 3 times 3. Okay, so 54 is the prime factors of 54 is 2 times 3 times 3 times 3. So, oops, I meant to do cube root. Excuse me. The cube root of 54. Yeah, just up here it had cube root. So we're going to rewrite this as with the prime factors, and it has 3, 3, 3, and of course there's 2. And we're looking for groups of n factors, and n in this case is 3. So we're looking for groups of 3, and we have a group of 3 in 3. So don't let the well, anyway. So we can cross out these 3 3's, and let's go ahead and cross those out. You can cross out those 3 3's and take that, one of those 3's, and put it out front. And then let's go ahead and rewrite it cleanly as 3 times cube root of 2. So, this is going to be the final form. Let's go through this one more time. So, I rewrote this as all the prime factors, and then I had a group of 3, so I could cross out those 3 3's and put one of them out front. And then just rewrote it cleanly. That's all I did. It was pretty simple. So, let's talk about what if we have variables instead of just numbers. Ultimately, you do the same thing, but you kind of need to think about it differently. With variables, factor out the perfect squares for square roots. Let's go ahead and okay, so with variables, you factor out the perfect squares for square roots. So what do I mean by that? Well, remember that the nth root of x to the n, so the nth root of, oops, not n to the n. The nth root of x to the n is going to be equal to just x. So that's going to be pretty important. This concept is going to be pretty important whenever we're actually doing it. So, as an example, let's take a look at square root of x to the 5th. Square root of x to the 5th. Okay, so let's rewrite this so that we have so we can factor out the perfect square. So the largest factor of x to the fifth that's going to be a perfect square is x to the fourth. If you just kind of think about that for a little while, you can kind of see what that means, what I mean by that. So, but as soon as I'm done writing this, I'll go ahead and explain it. So, square root of x to the fifth is equal to square root of x to the fourth times x to the first, or just x. Okay, so the reason I'm factoring out a perfect square because x to the fourth is a perfect square. In particular, it's a perfect square of x squared. So that means that you can rewrite this as square root of x to the fourth times square root of x. So what do we have here? We have square root of x to the fourth. Well, that's just going to be equal to x squared. So all I did was I factored out this x to the fourth because it's going to be the largest perfect square, and then whenever I did that, I separated them out so that we have x to the fourth. X squared instead of square root of x to the fourth times the square root of x. So I'm trying to remember if I wrote something. Okay, so what if it's not the square? So for nth root, factor out powers of n. So let's take an look at for an example of that. So if you have, say, the cube root of x to the seventh. Okay, so this is an example. Cube root of x to the seventh. So cube root of x to the seventh is going to be equal to, I want to write this out in a way where I can factor out powers of n. So a power of n, so n in our case is 3, so I want to write this as square root of x to the power of 3 times x to the power of 4. So x to the power of 3 times x to the power of 4. Well, and x, oh sorry, I forgot to put the 3. Okay, cube root of x to the power of 3 times x to the power of 4. So now this is something that I can work with, because x to the power of 3, the cube root of x to the power of 3 is going to be x. But I'm still not quite done. Before I even bother with that, I'm going to try to factor out as many powers of n, and as many powers of 3 as I can. So I want to rewrite this as x to the sixth times x to the first. So now I have x to the power of 6 times x, and this is also a x to the power of 6 is a multiple of 3, so we can take the cube root of this. What I'm trying to do is I'm trying to write this in a form where I can take the cube root of one of the factors. And in this case now I can. I can take the cube root of x to the power of 6 as say x to the power of 6 times, okay, so I have cube root of x to the power of 6 times the cube root of x. Well, cube root of x to the power of 6 is just going to be x squared. And then, of course, cube root of x, you can't simplify that any further, so it remains the cube root of x. Okay, so if you're having any, if you have, this is kind of strange stuff sometimes. So if you're, feel free to go back and rewatch anything. But otherwise, let's go on. We're going to go on to the other example. So let's go on to this example. It's kind of long. It's the fourth root of 80x to the fifth times y squared times z to the power of 7. Oh. Okay, so let's scroll up a little bit. So, fourth root of 80x to the power of fifth y squared times z to the power of 7. Okay, so let's first deal with this 80. Because remember, that was the first thing we did, was we dealt with just numbers. So, let me go ahead and copy this down. Okay, so we can rewrite this 80 as 4 2's. Oops. 2 red. Okay. Okay, we can rewrite this 80 as 4 2's and 1 5. Now, of course, we also still have the x to the power of fifth and y squared and z to the power of 7. Here, let's separate that out a little bit. Crud, what do I do here? Okay, so I just wanted to get this away from these three variables because we want to deal with this first. Now, so what do we have here? Well, we have 4 2's. So we can completely cross out those 2's. We can completely cross out those 2's and then put it out at the front. So now we have, now I'm going to go ahead and rewrite it on the next line, I think, as 2 times the square root of, sorry, not square root, the fourth root of 5 times x to the fifth times y squared times z to the power of 7. Okay, so let's put an equal sign just so we know that this is the same thing. Okay, so we have 2 times 5 times x to the power of fifth to the fifth and y squared and z to the 7th. Now, this part here is now where we go to the second part that we talked about. We're going to factor out powers of 4 out of these three variables here. So, let's rewrite this as, okay, we're still going to have the 2. Oops, that's the wrong section. We're still going to have the 2, and we'll have the fourth root 5, and let's go with x to the power of 4. Let's go ahead and write this out. So we have 2 to the fourth root of 5 times x to the power of 4. We're going to have 1 left after that x, after the 4 x's are taken out. And what's the most we can take out of y to the 2? Well, there's nothing we can take out. So y to the 2 is going to stay the same way. So then we have z to the power of 7. What's the most number of 4's that we can take out? We can take out one group of 4's. So that's going to be z to the power of 4 times z to the power of 3. Okay, so now we have, let's go ahead and rewrite this. Well, let's not bother to rewrite it. We have a group of, what we have here is a group of 4. And what we have here is a group of 4. So we can cancel these out, these two things out. And I'm going to go ahead and do that. I'm going to rewrite it as a separate line, though, just so we know what we're dealing with. So I'm going to go ahead and cross out this x to the fourth. so x to the fourth is crossed out, but after I do that, I need to go ahead and put it out front. So we have x is out front here. I'm going to go ahead and put this on a new line because this is going to... no, I think I can just scroll to the right a little bit. Okay, so now we have this z to the fourth, so we can put a z out front and cancel, or should say cross out, sorry, cancel the z to the fourth. So now we have 2 times x times z times the fourth root of 5x y squared z cubed. Or we can rewrite this cleanly. I'm going to do that on the next line as 2xz times the fourth root of 5xy squared z to the third. Okay, so let's put an equal sign. So then we have that 2xz times the fourth root of 5xy squared z cubed. This is the simplified form of this. I know this is one of those cases, kind of sort of rare cases, where the simplified version doesn't look a whole lot more simple than the original version. But this is the standard, and this is the way when you go on to other areas of math, you're going to want to have good standards so that things don't get confusing later on. So this is going to be so this is the final answer for this example. But now let's go on to another example. This is the last example of this kind, but then after this we're going to go on to adding and subtracting radicals. So one more example of this type. We're going to have the square root of... my page just fell down. Okay, the square root of 45a cubed b to the power of 8. Okay, so, and of course, well, I should say the instructions are simplify. Okay. So I'm rewriting this on the next line. So 45, we'll look to the left, 45a cubed b8, the square root of that entire thing. So just like before, let's rewrite this 45 as its prime factors. The prime factors of 45, you can do that using a factor tree if you want. In my case, I'm just going to go ahead and doing a factor tree, and this would be kind of annoying. So let's go ahead and I'll just let you know that it's 3 times 3 times 5. So it's 3 times 3 times 5, and then of course you still have the a to the power of 3, but I'm going to go ahead and I'm going to do 2 steps at once. I'm going to go ahead and write this as a to the power of 2 times a. And I'm going to go ahead and write this next part as, well, b to the power of 8 is already a square, so we're not too concerned about that. Okay, so now I'm going to go ahead and start crossing things out that need to be crossed out. The first thing is these two threes. I have a pair now, and this is a square root, so I'm looking for pairs, not triplets or quadruplets or anything, just pairs. So we can go ahead and cross out those two threes and then put a 3 out front. And let's go and do this on a separate line. Oh, whoops. Okay, so that way, just so you can see that you want, whenever you rewrite this, you want to have the room to put something out front. And we want, so, well, let's keep going. So then we have this a squared can be canceled out, can be crossed out, sorry, we're not really canceling anything. But once you cross that out, you need to go ahead and put it out front. So you have 3a. I think I may have just put the 3. Oh, yeah, I put the a at the wrong 3. Okay, so we have 3a out front. The 3 came from here. The a came from here. Now there's this b. Now, the b to the 8th is not just b squared, so we can't just cross it out and put a b out front, because what we have here is 4 groups of 2. So if we wanted to, and you don't need to do this, but you can rewrite this as b to the 4th, b to the 4th, the power of 2. This is, I mean, if you prefer to do it, that would work. If it makes it easier to understand, all you really needed to do was you need to divide 8 by 2. See, divide 8 by 2, and you'll get b to the 4th. But since I already wrote it out this way, this will work too. So then I can cancel the b to the 4th to the power of 2, and I'll have just a b to the 4th out front. Okay, so now, just like I said before, you want to write it more cleanly so that it can be more easily understood. We have this 3ab to the 4th is still going to be in the front. And then we're going to have the square root of, okay, so the 5 and the a are the only things that are left. So it's going to be 3ab to the 4th times the square root of 5a. And this is going to be the most simplified form. And in this case, you can kind of see that this is more simplified than this, kind of, sort of. And the reason why is because radicals are not simple. They're complicated. That's why we think of, since this has less inside the radical, we think of that this is more simplified, because we have stuff that's outside of it that's a little bit easier to work with. Okay, so that concludes the first section of using the product rule, but now there's also the next section, which is adding and subtracting radicals. Okay, so let's move on down. So when you're adding and subtracting radicals, what you're doing is you're combining like terms. Okay, so let's start out with, let's just go straight into an example. Let's say we have 7 times square root of 2 minus 5 times square root of 2 plus 3 times square root of 2. Okay, so we haven't really discussed exactly how this works yet, but we have done something that's very, very similar. Instead of combining these, let's combine like terms for a different problem. It's a different problem, but it's a related problem. Let's look at 7x minus 5x plus 3x. Okay, so this is pretty familiar. So we've seen this before. So 7x minus 5x. Okay, well, we have 3 like terms because they each have exactly 1 x, and they have the coefficients out front, but they have, in terms of variables, they have exactly 1 x. So 7x minus 5x will equal 2x, plus 3x will equal 5x. So this whole thing is equal to 5x. But do we remember exactly what x is? X is not just x. X, we call it a variable because it could represent it can represent a number. So we can say that x represents square root of 2. So that means we can rewrite this as 7 times square root of 2 minus 5 times square root of 2 plus 3 times square root of 2. And if square root of 2 is our x, then our final answer is going to be 5 times square root of 2. So this is going to be combining like terms. We just need to realize that we can treat like terms the same way that we do with variables. So Unfortunately, though, it's not always quite that simple, because sometimes we need to use the tricks we learned in the previous, just a few minutes ago, to simplify the radical before we can do anything else. So, let's take a look at this example. So we have the square root of 45, plus the square root of 80 minus 3 times the square root of 20. Okay, so at first glance, we don't really have any like terms here. Square root of 45 is not the same thing as the square root of 80. It's not the same thing as square root of 20. So we have three different terms. But what we can do is we can simplify each one of these. So we can rewrite this as a square root of 3 times 3 times 5. So, square root of 45, the prime factorization is 3, 3, and 5. And the next part is going to be, I'm going to go ahead and put this on a new line, I think. Okay, so 3, 3, and 5, and plus the square root of, I'm going to go ahead and write this as 2 to the 4th. Now I'll go ahead and write it out long ways. It means the same thing, but this is probably a little bit less confusing. So you have 2 to the 4th, and times 2 times 2 times 2 times 2 times 5. And then for this last part, you have minus 2 times 2 times 2 times 5 minus 2 times square root of 2 times 2 times 5. Okay, so now let's take a look at what we have on the inside. We have a pair of 3's here. So we can cross out those 3's. Cross out those 3's and put one out front. So 3 times square root of 5. And now we have 2 pairs of 2's over here. So there's one crossed out. Okay, so there's 2 pairs of 2, so there's one pair crossed out, another pair crossed out, and for each pair that we cross out, we're going to have to bring one out front. So that means we're going to have 2 times 2 out front, and we have exactly one pair out here. So we have one pair here, and don't forget to whenever you bring out, in this case, whenever you bring the 2 out here, don't forget to leave the first 2 you had still there, because that 2 doesn't disappear. So this 2 becomes this 2, but the 2 that you already had is still there. Okay, so now I'm going to go ahead and, as usual, write this a little bit more cleanly. So this is equal to 3 times the square root of 5 plus, I'm going to go ahead and combine these two 2's to make it 4 times the square root of 5 minus, and these two 2's I'm going to make it minus 4 times square root of 5. I mixed something up here. I'm not exactly sure what it was. Let's see. So I know what it was, but it doesn't matter. So we can keep going. The original problem had a 3 here. That's why I'm confused. I miswrote it, but you know, we can still do this. This is still salvageable. So what we have here now is 3 times square root of 5 plus 4 times square root of 5 minus 4 times the square root of 5. And so this plus 4 minus 4 will combine to make 0. So we'll have, and then 0 plus 3 will give you 3 times the square root of 5. And then this is going to be the final answer. This is as simplified as it comes. Okay, that concludes this particular lecture. I will see you in the next video.